start with the last lecture.
Okay. So I will recall some of the things we have been using. We started with a compact metric space XD, and we took a continuous semi-metric phi X. We defined phi subsolutions with the function U, which satisfy the Lipschitz condition with Lipschitz constant 1 with respect to phi. The set of subsolution is noted by S sub phi. We define concatenated cost. I'm not going to recall what they are. And the pair barrier is the limit of this concatenated cost as eta goes to plus infinity. It's also the soup because it's not phi eta is not decreasing in eta. The Aubry set was defined as a set of points such that phi infinity of xx is 0. And with this, we define phi solution as a set of phi subsolutions which satisfy the following condition for every x in x. There exists a y in x and then eta positive such that ux minus uy is phi of eta x. Phi of eta yx, sorry. So the set of solution is a subset of the set of phi subsolution. And in fact, if U is a phi solution, we can improve the equality in the definition by, and in fact, for every x in x, we can find y in the Aubry set such that ux minus u infinity is phi infinity of yx. And because y is in the Aubry set, it's also phi of yx. The phi solutions are stable by uniform convergence, and we prove the representation formula. If U is a phi solution, then U of x is the infimum of Uy plus phi of yx, y taken only in the Aubry set. So the mother relation was defined as this by x is mother related to y if and only if phi x plus phi xy plus phi yx is 0. The graph, okay, is denoted by graph mother of phi. And for every phi subsolution and every xy in the graph, okay, we had that for every xy in the graph, we had u of y minus u of x is phi of xy. So instead of having inequality, we have equality when the pair is in the graph of the mother relation. We said that the phi subsolution is strict if, in fact, the set of points xy, where uy minus ux is phi of xy, is exactly the graph of mother. It's always contained, but you are asking one more condition, equality. And we ended lecture 3 showing that there exist strict subsolutions. Okay. So we will need the following result, which I didn't do last time, but which is easy to do. The subset of strict phi subsolution is dense in the set of all subsolution of the topology of uniform convergence on the compact space X. And we showed that there exists at least one strict subsolution. So if you start from any other subsolution and take the complex combination, yn minus epsilon u plus epsilon u0, it's a phi subsolution, but because phi subsolution are stable by complex combination, but if you take epsilon positive, you can show that it's strict phi subsolution. And of course, when epsilon goes to 0, u epsilon goes to u in the topology of uniform convergence of the compact X. Okay. So because I want to say something about the maximum principle, I need to define a notion of super solution. Okay. A continuous function is a phi supersolution at x if, well, we can find a y such that ux minus uy is larger than phi eta yx. Okay? A continuous function is a phi supersolution on x if it's a phi supersolution at every x. We will denote by S sub phi the set of phi supersolution. Now we have to impose continuity because it doesn't follow from anything here. Contrary to subsolution, okay, they were automatically continuous. Now, if we have a phi subsolution, we saw that in lecture 3, that satisfies the inequality here. Okay, then in fact it's an equality. Okay, it's because you have phi of yx is larger than this quantity in this case, and therefore, because phi eta is larger than phi, everything is equal. So a function is a phi solution if it is both a phi subsolution and a phi supersolution. Okay. And of course, if you have a continuous function, it is a phi supersolution at every x of the Aubry set automatically. Okay. Why? Because for every sec in the Aubry set, and for every eta non-negative, you have u of x minus u of x is phi eta of xx, which is 0 because that's in the Aubry set. Therefore, to check that a continuous function is a phi supersolution, it suffices to check it at the points outside the Aubry set. Now, notice that when the Aubry set is the whole of x, this implies that every continuous function is a phi supersolution. So it's not a great concept. Okay? This notion of phi supersolution will not coincide in general with the notion of viscosity supersolution when phi is the Magnus potential of a Tonelli Lagrangian. Okay. But still, it is convenient for phi solution to be function with some phi subsolution and phi supersolution, so it's nice to have at least a concept of phi supersolution. In fact, if you look at viscosity theory, subsolution and supersolution are not the same. There is very little things that you can say on supersolution, but on subsolution, you can say a lot when the Hamiltonian is convex. In subsolution, in some sense, you only use them for solution. Supersolution, you only use them for solution. Okay? Okay. When phi, however, when phi is the Magnus potential to Tonelli Lagrangian, the phi subsolution and the phi solution are the same as the ones given by the viscosity solution. And solution notion of the associated Hamilton-Jacobi equation, I'll show you that today. Okay. And of course, you have the same kind of thing that if you, for x0 in x, the phi subsolution phi of x0 dot is a phi supersolution at every x different from x0. In fact, we proved it's a phi solution at every x. Okay. And it's a phi supersolution on the whole of x if and only if x0 is in f5. It's the same proof that we did in lecture 3. So, and again, we can give a characterization of phi supersolution in terms of the Aubry set. So U is a phi supersolution if and only if for each x in x, we can find a y in the Aubry set such that ux minus uy is larger than phi infinity yx. Same proof works, in fact. Okay. So the maximum principle, we can now go to that. So we start, of course, with the first case, is that if we have a strict phi subsolution and U and V is a phi super solution, then if U minus V reaches a global maximum at X, then X is necessarily its own reset. Okay? So since phi is, so let me show that. So when U is a strict subsolution, this forces the maximum to be attained only on the Aubrey set. Because V is a super solution, we can find a Y in X and an eta positive such that Vx minus Vy is larger than phi eta Yx. Definition. Okay. Now, because U minus V reaches a global maximum at X, we have Uy minus Vy is less than Ux minus Vx, which we can rewrite as Vx minus Vy is less than Ux minus Uy. Okay, so we combine this with the fact that phi eta is larger than phi, with the equality here defining phi super solution, and the fact that U is a phi subsolution to obtain the following things. So phi Yx is less than phi eta of Yx. This is because phi eta is non-decreasing in eta and phi 0 is phi. And so this is less, phi eta of Yx is less than Vx minus Vy, which is less than Ux minus Uy. And this is less than phi Yx, okay, because U is a set of subsolution. So in fact, we get the equality phi Yx is phi eta Yx is Ux minus Uy is phi Yx. Now, this implies that xy is in the graph of the Mather relation because U is a strict subsolution. Okay? So we showed that Yx is in the graph and phi y is equal. Phi Yx is phi eta of Yx. Okay? But Yx is in the graph of the Mather relation means that phi xy plus phi Yx is equal to 0. Okay? So now we get 0 is phi Yx plus phi xy plus phi Yx. But we showed that phi Yx is phi eta of Yx. And now we use the triangle inequality in the stronger sense obeyed by the family phi eta to get that this is larger than phi 0 plus eta of xx, which is phi eta of xx. This one is itself larger than phi xx, which is equal to 0. So we have equality everywhere. Okay. So we found some eta positive for which phi y of xx is 0, and we showed the second lecture that this implies that x is in the Aubrey set. Okay, now suppose we have a phi subsolution and a phi super solution, then the maximum of the difference is attained on the Aubrey set. Okay, so this is the maximum. You found the set on which maximum is realized. So as we saw above, this holds when you use a strict phi subsolution. And we observe that the strict subsolution are dense in the set of subsolution. So this equality is valid everywhere of subsolution. Okay. So this shows that we indeed have the right version of the maximum principle, of which we could deduce, of course, the representation formula, which we deduced anyway before. So now I want to compare weak KM theory for Tonelli-Lagrangian and weak KM theory for metric space. So I want to show that when I take as semi-metric the Manier potential of a Tonelli-Lagrangian at the critical level, then the weak KM theory of metric spaces and the weak KM theory of Tonelli-Lagrangian gives me exactly the same object. Okay, so let me go back a little bit to the framework I introduced in the beginning of lecture 1 to motivate weak theory on metric spaces. So we suppose that MG was a compact Riemannian manifold. We denoted the norm on tangent and cotangent space at some x by norm at x. And if we had an absolutely continuous curve, the J length was integrating the norm of the speed here as usual, and the distance is obtained by minimizing length of curve joining the point. Now, the definition of a Tonelli-Lagrangian. The Tonelli-Lagrangian is a C2 function defined on the tangent bundle that satisfies the C2 strict convexity in speed. So for every xv in the tangent bundle, the second partial derivative with respect to v is definite positive. So this is, of course, very strong convexity of L in V. And we had the uniform superlinearity that for every k, we can find C of k such L of xv is larger than kvx plus ck. This is the same thing because of the compactness of M, that L of xv divided by norm of V goes to infinity, as the norm of V goes to the infinity uniformly in X. So if we take an absolutely continuous curve, the action is just the integral of L on the speed curve of gamma. And for t positive, we define ht as the infimum of actions of curve joining x at time 0 to y at time t. So this is the minimal action needed to go from x to y time t. Tonelli's theorem states for Tonelli-Lagrangian that the infimum defining ht of xy is attained by the action of a curve as smooth as L. Okay. Since we can shift parametrization and the Lagrangian does not depend on time, ht of xy is also the inf over all curve joining x to y, okay, parameterized by an interval of length. That doesn't change anything. So the Manier potential for each number C in R, we can define the Manier potential phi sub C, and it is defined as the infimum of for t positive of ht of xy plus ct. Okay, so this is the Manier potential. It can be finite, infinite, okay, but with okay. So we use the definition of ht of xy to conclude that if we take the action of a curve parameterized by AB and starting at x and ending at y, and the length of the interval is t, then the action plus cb minus a is the integral from a to b of gamma s, gamma dot s plus cts. It's larger than the inf here. Okay, so it's larger than phi c of gamma a to gamma p. So in fact, if we want to compute phi c from point x to point y, we can just take the infimum of all curve joining a x to b of a curve parameterized by time, okay, by an interval of length t exactly. Now here is a proposition. There is a unique constant C0 such that the Manier potential is identically minus infinity before and is everywhere finite for C larger than or equal to C0. And moreover, the Manier potential is Lipschitz. So it's continuous. This constant C0 is called the Manier critical constant. Now, first thing is C0, L of X0 plus C0 is non-negative everywhere for all X in M, okay, if C0 is a Maillet critical constant. So we take the constant path at X, its action, so at this X where L, okay, its action, because it's a constant path, the speed is 0, is exactly B minus A L of Lx0, okay? Gamma starts at X and ends at X. Therefore, the action of this curve modified by C0 is larger than phi of C0 XX, which is 0 because we said that phi C0 is a semi-metric in that case. Now, of course, this is true for A and B, so it gives you that Lx0 plus C0 is non-negative. Now, we come to the Hamiltonian. The Hamiltonian is defined by h of xp is the soup of p applied to v minus L of xv for v a tangent vector at M. And because L is Tonelli, not only the Hamiltonian is finite and continuous, but the soup in the definition above is attained. Okay. And the Hamiltonian is C2 and also Tonelli. From the definition of H, okay, H xp is the soup of a whole V of PV minus L of xv. So we get this potential inequality, and this potential inequality is an equality if and only if P is the partial derivative of L with respect to V at xv, or if V is the partial derivative of P with respect to H at xv. Now, for a given x, since h of xp is convex in P, it achieves its minimum at P0 if and only if the partial derivative with respect to P0 is 0. Okay, but if the partial derivative here, P0, is 0, well, then we have equality in the function. Equality, but P0 0 is 0. Okay. And therefore, we get L of x0 is equal to h of xp0. Okay, so this is the minimum of h of xp in P. Okay. So we get that the minimum is minus L of x0. The minimum of h, okay, in P is minus L of x0, and it's achieved exactly at P equal the partial derivative of L with respect to V at x0. So we get h of xp is larger than minus L x0, okay, which is also the minimum of h of xp bar. So any number above that one is attained by h. Okay. So in the same way, we take a semi-metric, not phi 0, but phi sub C0, so the critical Maillet potential. Okay. Now that we have a semi-metric, we can define its pair barrier, phi C infinity, phi infinity, okay? And we can define the Aubry set of phi as a set of x in M, such that phi infinity of x is 0. There is a pairs barrier associated to the Lagrangian L. It's obtained by, instead of taking the sorry, here there is a C0T. So the definition is h C0 of xy is the lim as t tends to plus infinity of h t of xy plus C0t. Okay? And this pairs barrier is always finite. You can show that it is always finite. And the Aubry set for the Lagrangian, or rather its projected Aubry set, is defined as the set of points where the pairs barrier HC0L from X to X is 0. Okay? Now I'm going to give some known facts from the Wittgenstein theory of Tonelli Lagrangian, and they are the analogs for Lagrangian of the result we obtain for semi-metric. Okay. If you have 2 points, x, y, and one of them is a Aubry set, then the pairs barrier between them is equal to the Manier potential, okay, like we showed for the case of the semi-metric. And for every xy in M, we can find a z in the Aubry set of L, such that the pairs barrier from x to y is the pairs barrier from x to z, plus the pair barrier from z to y. And this is, of course, by the previous result, the sum of the Manier potential from x to z plus the Manier potential from z to y. So the next two results define viscosity subsolution and viscosity solution. So, in fact, I mean, it's not a definition, but I identify. We have the same thing, is that U is the viscosity subsolution of x of dxu equals C0, if and only if U of y minus U of x is less than the Manier potential at C0 from x to y, okay? And the second thing is that we have the representation formula for viscosity subsolution, for viscosity the viscosity solution, not subsolution. Viscosity solution are identified as satisfying. So the viscosity solution of h of x dxv equals 0 equals C0 are exactly the function v which satisfies the representation formula, and here it should be a v, not a u. Okay. They satisfy the representation formula with y in the Aubry set. Okay, exactly like we have shown for the case of semi-metric. Okay, we'll need the following result on the Aubry set to be able to identify this Aubry set of A5. We will need to understand a little bit the structure. The Aubry set, in fact, it's an equality. By the end, we are only going to use the fact that it is Aubry set is contained in the union of the two sets, and in the end, we are going to show that they are all equal. But I could do it right now in the lemma, but I don't want to spend too much time and repeat the argument. So what is BC0L? It's a set of X such that I can find a Y such that XY is in the graph of the Mather relation. Okay, I can find a Y different from X such that phi C0 of XY plus phi C0 of YX is 0. Or if I'm not in this set, I am in the set of X where L of X0 plus C0 equals 0. Okay, remember we showed a little bit before that this quantity for every point x was non-negative. So it may be attained at some point, and if the point where this quantity L of x0 plus C0 is minimum, the mean is equal to 0, is also in the Aubry set. In fact, this represents the stationary point of the Lagrangian flow or the Hamiltonian flow, which are in the Aubry set. You can understand that this is not exactly the same thing. The situation from the dynamical point of view is not exactly the same. If you have a fixed point or a point which is not fixed. So we will show that for x in the Aubry set, if L of x0 plus C0 is not different from 0, then x is in the other set PC. That's what we need to do. Now, because we are assuming x is in the Aubry set, we have hc0 of xx, which is the limit as t goes to infinity of ht of xx plus c0t is 0. Therefore, I can find the sequence Tn increasing strictly to plus infinity, such that the lim inf of htn xx plus c0tn is 0. Okay? But by Tonelli's theorem, each of these htn xx is the action of some curve joining x to x in time tn. So I can choose such a curve. Okay? I choose a curve gamma n, which gives me this minimal action. And therefore, I get this curve gamma n from 0 tn to m with gamma n0 equal gamma n tn equal x. And the action k of L modified by C0 goes to 0 as n goes to infinity. Now, I'm going to show you that there is an open neighborhood of x such that for n large enough, the image of the curve, the path of the curve gamma n, intersects the complement of V. Okay? So the curve cannot stay arbitrarily close to V. They will have some point leave a fixed neighborhood of x. Now, we showed earlier, as I said, that L of y plus C0 is non-negative, and minus L of y0 is the infimum of h. Okay? Since we are assuming that L of x0 is different from C0, we must have minus L of x0 is strictly less than C0. Okay? Because it's positive inequality there. And therefore, the infimum of hxp, which is minus L of y0, is strictly less than C0. Okay? So if the infimum is less than C0, I can find a P0 such that xp0 is strictly less than C0, and I take an A between them, strictly between them. Now I can always, so the P0 is a covector at x, I can always find a smooth function, C infinity if I want, whatever, at least C1, such that the derivative of u at x is P0, okay? Now, by continuity of the derivative, y u is smooth, we can find an open neighborhood such that hy dyu is less than a, strictly less than c. Okay? Now, from the Fenchel inequality, we get that the derivative, if y is in V, and P is a vector tangent at y, dyuv plus C0 minus A. Okay, so this is by the Fenchel inequality less than Lyv plus Hx by V. And I still have the C0 minus A. But now h of x dyv is less than A. No, it's dyu here. Sorry. dyu. Okay, and from the inequality above, this is less than A. Okay, and therefore I get that the three terms here are less than LYV plus A plus C0 minus A, which is L plus YV plus C0. Okay. So if gamma n of 0 Tn is included in V, we just have established this inequality here. Okay. The derivative of y at u applied to V plus C0 minus A is less than L of y. V plus C0. Okay. This inequality is valid for all y in V and all tangent vector at y, and therefore we can apply it along the curve gamma n to get the derivative at gamma ns of u applied to the derivative of u at gamma ns applied to the speed of gamma n at s plus C0 minus A is less than the Lagrangian evaluated at point S of the speed curve of gamma n plus C0. And this is valid for every S because the curve is inside V. So we can integrate this inequality between 0 and Tn, and we take into account that if we integrate the derivative of a function, we get the difference of value between the endpoints. Both endpoints are at x, so we get 0. Okay? So finally, we get C0 minus ATN is less than the action of gamma n, okay, modified by C0. But this action goes to 0 by choice of the curve gamma n and of the time Tn. Okay? And the other one here goes to plus infinity because C0 is strictly bigger than A. So this cannot happen for all Tn. It happens only for a finite number. Okay? And therefore, when n is large enough, the path of the curve intersects the complement of P. Now, dropping the first few if necessary, for each n, we can find a time such that the curve gamma n at time Sn goes through m minus v. What do we get? We estimate phi of C0xx, okay, is less by the triangular inequality than phi 0 of x gamma n Sn plus phi 0 of gamma n Snx. So this manier-potential between the 2 points x of gamma n Sn is less than the action modified by C0 point of a path joining them, which is the case of the path gamma n going from 0 to Sn. Okay, so I find the first inequality here. And the second one is less than this one, because the rest of the path goes from gamma n of Sn to gamma n of x, of Tn, which is x. Okay, now if I add these two, I just have the action, and this goes to 0. So this is 0 less than the sum goes to 0. It tells me that the sum phi 0 of x gamma n Sn plus phi 0 of gamma n Sn x goes to 0. Okay? Now the gamma n are all contained in the compact set m minus v. Okay. I did choose v as the neighborhood of x, and therefore I can extract and find the limit point in m minus v. So if I look at this inequality here, because phi 0 is continuous, phi C0 is continuous, I can pass to the limit, and I get phi C0 xy plus phi C0 of yx equals 0, but y is not equal to x, because x is in V and y is not in V. So this tells me precisely that x is in the other state, BC0L, which was defined as the set of point X for which you can find a Y like that and Y different. Okay. Now I can start to compare the pairs barrier obtained from the semi-metric and from the Lagrange. So we always have that the pairs barrier of the Lagrangian is less than the pairs barrier of the semi-metric phi, which is, of course, the critical Fourier potential phi sub 0. So this will force, of course, the Aubry set of phi to be included in the Aubry set of L. Now, fix x and y in x. If phi infinity of xy is plus infinity, there is nothing to. In fact, we are going to show equality, and because we know that h of c0 is finite everywhere, this case does not happen, but a priori. Okay. Now we know that phi infinity is everywhere finite. So I claim that for every eta and epsilon positive, I can find a curve. Okay. Gamma, eta, epsilon, which start at x and ends at y, and such that the length of the curve is at least eta. And here, sorry, this is not correct. I should always modify by c. So here I should have the action gamma, eta, epsilon plus c0 t eta epsilon is less than phi infinity of xy plus epsilon. Okay? Okay, to prove the claim, fix eta and epsilon. Since phi eta of xy is less than phi infinity of xy, from the definition of phi eta, we can find a chain starting at x0 and ending at y, such that the cost of the chain for phi is less than phi infinity of xy plus epsilon over 2 or phi eta. Okay, we can find a chain such that with a cost less than phi eta xy plus epsilon over 2, and the length of the chain is at least eta. So this is the definition of phi eta. Okay, from the definition of phi, and again here there is a missing, we can find a path connecting xy in some time ti, so connecting and such that L of gamma I plus C0 ti is less than phi of xi plus 1 plus epsilon. Okay, this is because phi is the Manier potential. So because gamma I connects xi to xi plus 1, the length of gamma I is at least the distance between the endpoints. Now we take gamma eta epsilon as the concatenation of these curves in that order. Okay, we find again there is a C0 missing here. Okay, there is a C0 Ti missing here. So, and here there is the C0 So there is a C0 TI missing here. And this is less than Cx0 x and x1 xn plus epsilon over 2. Okay, so we get that this is less than the action of the path gamma eta epsilon modified by C0 is less than phi infinity of xy plus epsilon. Okay, and of course the length is larger than the sum of the length, is equal to the sum of the length, which is larger than the distance between the endpoints. So it's larger than eta. So this finishes the proof of the claim. To finish the proof of the lemma, we need to use the superlinearity of L, but only for k equal 1. Okay, so this is like more like the it's growing to infinity with V. It's coercivity, it's not really superlinearity that we are using here, but we needed the superlinearity to be able to use, for example, Tonelli's theorem. But anyway, so this implies that for any path, we have that the length, the action of gamma is larger than the length plus C1 B minus A. Okay, so we apply this inequality to the path, and here again there is this C0 missing all the time. I started to do the notes with C0 equals 0, and then I suppressed it, so it's missing everywhere. Oh no, here there is no C0. No, sorry, here there is no C0. This is correct. The action is larger than the length. Here it's correct. But we know that the length is larger than eta, and this is larger than, oh no, there is a C0. I'm sorry, there is a C0 everywhere. Because of the first inequality. Okay, so here we get the C0, in fact, at the end. So what we get is that by, sorry. So in the end, because I forgot about the C0, we obtain plus infinity is larger by infinity of xy plus epsilon, larger than the action of gamma eta epsilon plus C0, the time of parameterization of gamma and epsilon. So this is larger than the length gamma eta epsilon plus C1 plus C0 T eta epsilon. Okay? So for each eta, we got such a thing, and here this is larger than eta. This one is larger than eta. So if we let eta go to infinity, the sum of these two quantities is bounded. This one goes to infinity, so that eta epsilon has also to go to infinity. And this has to be negative. Okay. So this is what we get. Okay, there is again. So here there is again a C0 T missing. So we get this lim inf here is less than phi eta xy. Again, we have to modify the action by C0, but so this is less than the lim inf of xy, and this is less than phi epsilon of xy because it's all bounded by this term. But this is exactly the pairs barrier for L. So we show this inequality. Sorry for the mistake. Okay, now the next step, we already know that A phi is included in AL. We want to show equality. I will do that after using this to prove the consequences of this. So already with this theorem, we know that the two concepts of Aubry sets give the same set. We want to show that the viscosity solutions are identical to the phi solution. Okay? Of course, the subsolutions are the same, as we will see. So let's start with the subsolution. The viscosity subsolution of h of x dx u equals c0 are exactly the functions u that are subsolution for phi, with phi equals phi c0. In both cases, the viscosity subsolution and phi subsolution are the functions u that satisfy uy minus ux in the case of viscosity subsolution less than phi c0 of xy, and in the case of phi solution less than phi of xy, but the two are equal by choice. So the subsolution is the same. And again, now let's deal with the solutions. The Hamilton-Jacobi equation, they are exactly the phi solutions, okay. And the viscosity solution are exactly the viscosity subsolution, or equivalently the phi subsolutions that satisfy, and here again it's a V and not a U, that satisfies the representation formula for phi C0. Okay, so here it should be, let me maybe write that down here. Vx equal infimum for your A0L but this quantity is the same as phi of yx by definition, okay, but and V is a subsolution for phi, and this representation formula defines exactly the phi solution, okay, as we saw, because solution satisfy the representation formula. Okay, and of course the two Aubry sets are the same, so we are taking over the same y's. Okay, so we got that the viscosity solutions are the same as phi solutions. And now we are going to prove also that the two pairs barrier are the same. We showed the inequality, this one before, and it remains to prove the converse inequality. As we said before, HC0L is everywhere finite. So if we fix x and y in X, we can find Z in the Aubry set for L. Yes, that's what the lemma again, which, by the way, is the same as the Aubry set of phi. Now that we have clicked the theorem, such that the pairs barrier for L from X to Y is the same as the sum of the pairs barrier from X to Z, plus from Z to Y, which is phi C0 XZ plus phi C0 of X1, of ZY. Okay? Now, because phi is equal to phi C0, and Z is in the Aubry set of AL and also of phi, we get that H C0L of XY is phi of XZ plus phi of ZY. So this is phi infinity of XZ because C is in the Aubry set plus phi infinity of ZY, which by the triangular inequality is larger than phi infinity of XY, which is what we wanted to show. Okay? So we showed, once we prove the equality of the Aubry set, we get the equality of the notion of super solution and also the equality of the pairs barrier. Now we give the proof of that fact. We already showed that Fi is included in AC0L. So we need to prove that AC0L is included in Fi. Now, to prove that, we recall that AC0L is contained in the union of the two sets, BC0L and EC0L. Okay. Typing problem here. Okay, where BC0L is a set of X such that there exists Y different from X, such that phi C0XY plus phi C0 of YX is 0. Okay. And EC0L is a set of X such that LX0 plus C0 is equal 0. So we'll show that the union of these two sets is contained in Fi. Okay. That will give us the inclusion. AC0L is in Fi, but we already showed that Fi is in AC0L, so they will be equal, and also equal to this one. So that proves, as I said before, that inclusion AC0L is included in BC0L union EC0L is in fact an equality, but we don't need it to do the proof. Okay, why is BC0L contained in Fi? Because if we take any xy in X, we write phi yx plus phi xy plus phi yx. Well, phi yx is phi of x txy. If we take eta up to the distance from x to y, the phi eta does not change, as we have seen in one of the first lectures. And same thing, it's also phi of txy yx, so it's larger than phi 2txy xx by the triangular inequality. Okay. Now, if x is in BC0L, we can find then y. So this will be with this 0. So we will get that this is 0. Okay. But y is different from x, so the distance is positive. So we found an eta positive such that phi eta of xx is 0, so x is 0. So this shows it. And it remains to show this one. EC0L is included in Fi. The main idea is due to Antonio. Okay. So, as I said, EC0L is included in the set of X such that LX plus C0 in 0, and then we show that this last set is included in the Aubry set of 5. Now, fix x in M such that Lx 0 plus C0 is 0. The argument is local, so we identify a neighborhood V of x in M with an Euclidean space, and we will use the Euclidean norm and the Euclidean distance on Rn, which is that open neighborhood of x. Now, L is C2. Okay, so I can write a first order Taylor development if I restrict on the compact set, okay, the product of the Euclidean ball of center x of radius 1 with itself, with a remainder which is bounded by k, the distance squared between the 2 points. Okay, I'm just writing here a Taylor formula, and the second order is, of course, term is bounded by k times the distance for some constant. Okay. Now I am assuming that L of x 0 plus C0 is 0, but L of y 0 plus C0 is non-negative everywhere. So that tells me that the derivative, partial derivative, with respect to x of Lx0 is 0. Okay? So I can forget this term here. And also Lx0 plus C0 is 0. I can forget this one. And so I get that Lyv plus C0 is less than the linear map fixed, because x is fixed, partial derivative of L with respect to V at x0 applied to V plus k times distance squared. And this is true for every Yv in the product of the two, the compact set. Now fix V0 in Rn of norm 1, and for any integer Mn, consider the path gamma Mn parameterized by the segment 0, 2 divided by n with value in the Euclidean ball of radius 1 around x, okay, which has the property that at 0 and 2 over n it's at x, and at 1 over n it's at x plus 1 of Mn V0, and between the points it's Fi. Okay? On each one of the two it's an interval. So this is what you have. This formula. You go from x to 1 over Nm V0, and here you decrease from 40 equal 1 over n from x0 plus 1 over Mn V0 to x. Okay. So the derivative on the first interval is constant, is 1 over m V0, and the second one is minus 1 over m V0. What is the distance of gamma nt to x? Well, you just look, it's less than 1 over Mn, which is less than 1 over m, which is less than 1. So indeed, the path goes in the unit ball around x. And the derivative, okay, the speed at t, is plus or minus V0 divided by m, which is equal to 1 over m, because V0 is a unit vector and it is less than 1. So the speed also is in the ball of radius center 0 and radius 1. So from, no, here it's a 0, it should not be an x. So it's 2. There is some misspellings here. X is not in the tangent space, it's 0 that is in the tangent space. Okay. So we get, because these two quantities are one in the ball of center x and radius 1, and another one in the ball of center 0 and radius x, that it should be here, we get that the Lagrangian plus C0, okay, is less than the linear map, okay, which is independent of t, partial derivative with respect to of L with respect to x0, applied to the speed plus a second order term, which is k times the distance squared. Now, this one remains as it is, but here what do I have? Well, I just look at both here and here, it's less than 1 over m. And therefore I get less than 2k over m squared. Now I integrate the inequality we just obtained on each one of the two intervals and take into account what are the values of gamma m at 0, 1 over n, and 2 over n, and what are the speed of each one of the interval. Okay. So I integrate between 0 and 1 over m, I get less than the plus C0, sorry. There is again a C0 1 over n, which is missing. Okay. Oh, no, no, no. Yes, that's correct. And here, what I did bound, here it's not L gamma nt, gamma dot nt, but it's plus C0. Let me just show you. Let me get back to show you that I'm not cheating here. So this what is bounded by the linear term plus the second order term. Okay? So here there is a C0 in the formula here, and therefore we get exactly that the Magne potential between x and x0 plus v0 over mn is less than the linear map evaluated at v0 mn, because you integrate this first term, which is constant, on an interval of length 1 over n, okay, plus here you integrate on an interval of length 1 over n, so you get another. Okay, so you get that. And moreover, the distance from x to x plus v0 over mn is 1 over mn. So if you now we don't want as distances over the Euclidean ball, but we want as distance to do evaluation with Riemannian metric on M. But on this compact subset, the two metrics, the Riemannian and the Euclidean, are Lipschitz equivalent, so I can find a row positive which compares the two distances. Lipschitz constant, okay. So this implies from this equality here that the distance between x to x0 plus v0 over mn, but now the Riemannian distance is larger than rho over mn and less than 1 over rho mn. Okay, it's this one that interests me on the left one. So what do I get? So this chain satisfies that the length of the chain is larger than twice the distance from x to x plus v0 divided by mn, So it's larger than 2 rho divided by Mn. But it's also true that it's larger than rho divided by Mn, but it's 2 rho Mn here. Okay, twice what I found. And what is the phi cost of the chain? I just add the 2 phi costs that I found. Okay, it was this linear map applied to P0 divided by Mn plus K, 2K divided by N M square. These two cancel out now because you go V0, you come back minus V0. When it's linear, they cancel out. And you remain with 4K NM square. Okay. So what does this tell you? The chain here it's 2 rho Mn. Found a chain of length at least 2 rho Mn and cost at most 4K NM square. Okay. So you get that phi 2 rho divided by Mn xx is less than 4K Mn square. Now, if you want to compute phi of 2 rho xx, because here you divided by Mn, you have to multiply the cost by Mn. Okay, and this is less than 4K divided by M. Now, M is arbitrarily larger than 1, and therefore, you get, because you know this quantity is non-negative, it's bounded by something which goes to 0, so you get that this quantity is 0. So this implies that X is in the Aubry set of phi. So this phi has to show the desired EC0 included L, included in A phi, and we conclude that we have the equality also. And that's all. Thank you.